Okay, I think we can start.
Okay. A very good evening to everyone. So today we are going to read a paper by Max Collinet and others. It is basically about a thermodynamic modeling platform or software called MAGMARS to understand the evolution of the Martian mantle and the FeO-Rich peridotite.
Yeah, I will add a thing. So could you turn to the last page? Okay, yeah, could you turn to the last page? The first page. The first page. So I think Max Collinet is working with Doris Brewer at the German Space Aerospace Center. So Doris Brewer, she holds I think she probably holds some leadership position at the German Aerospace Center, and she's in charge of several missions before. I forgot the details. But she's also working on experimental petrology. So this work is um, basically they're trying to investigate the Martian magmas. But a lot of methodology is almost the same as what we would apply to Earth. Um, and also, I think Max Collinet probably he got his PhD working with Tim Grove. So Tim Grove himself is an experimental petrologist at the MIT, and he's was member of he's a member of National Academy of Sciences, and Tim Grove has made a lot of contribution in different thermodynamic models. So this is just another product out of Tim Grove lab. Okay, so go ahead, Arka.
Okay. So Max Collinet, like Dr. Zhang said, he did his PhD in 2019 from MIT and presently is at the German Aerospace Center doing his postdoc. His research interests are mostly magmatic petrology. He works as an experimental petrologist. His focus of interest is of study of meteorites and high temperature experiments. And in particular, at present, he is working uh, on the evolution of Martian mantle. And this is on 2015, he made a publication. And this is a continuation of his work on the same thing. So as we move on to the paper, the paper actually approaches to study the Martian mantle, understand its evolution. Uh, so what happens? So as the rover that from the rover we get a lot of we get the chemical composition of the surface samples over there. So since then, people have been trying to uh, mimic the melting models for Martian mantles to get the surface composition. This paper, so this is basically the way they have worked.
Okay.
So
Let me add some more information to our participants. So, um, let's start from some observations. So, what the people observe, this basically came from two major, let's say, well, for the rovers, there are basically several part of that. For example, the Vikings, I think that's 1990s. That's a rover on Mars, basically hanging around, uh, and then Curiosity, and and I think that's what's that 2010s, 2010s. So also I've been walking around, and then let's say InSight mission. InSight mission is 2018. So that's with some of the major missions that with some landed rovers that are walking around Mars. So what people get from the petrology perspective is that they find that Martian basalts with a relatively high concentration of FeO, or with about I think 18%, something like that. Not exactly for Mars, and then for the Earth, the FeO is approximately 9%. So it's about half of the Mars, and then for the moon, that's about, in my recollection, that's about 12%. Correct me if I'm wrong. So 12% for the moon, I think. Then for Mercury, so that's very close to the sun is about 2%. So for all these terrestrial planets, they or planetary bodies, they all form a metallic core and a silicon mantle. So you may ask that where is Venus, which is another one. So far, I don't think people know this very well, because Venus, the atmosphere is covered by it's a very thick atmosphere. The carbon dioxide is 95%, and also it's atmospheric pressure is about 100 times of that of Earth. So it's very hard to land the rovers, and also because there are satellites, artificial satellites, humans sent to constantly collect different spectrals from these different planetary bodies. And this is sort of, let's say, self-consistent, first to the first degree coming from that, and then from the rover, and third from the return missions, which now we only have on the moon, but soon we are going to on Mars very soon. All this different composition for FeO, a very crucial part is that they mean the very different oxygen fugacity of a different terrestrial planets. So basically, you could interpret in an easy way is that the higher FeO content they have in the mantle, then that means the more oxidized the planet could be. Because if the planet is very reduced, then the iron would prefer to go into the core as Fe, which has as iron. An iron metal, pure iron, elemental iron metal has a valence state of 0. And FeO or Fe2O3, then its valence state is either 2 or 3 plus. So by that, it's very important to refer to the fugacity of these different planets. That's only the first order for that. But here, there's another thing that, okay, people saw the Martian basalts, for example, is about 18 or 19% of FeO. So how about the mantle? Because those basalts, Martian basalts, basically they are being the products of the partial melts of the mantle. So we need to know the mantle FeO, because that's the bulk mantle composition that people are interested in. So by that, then people need to figure out, and as this paper pointed out at the very beginning, there are two ways that people could do that. Actually, it's interesting because at the turn of the 21st century, when people just analyzed the Martian composition, people were debated what the source composition could be. For example, one group like Mark Griswold's group, what they have been applied for using the software called MELS, which they also mentioned in this paper, show that I think there's a very limited fractionation of FeO, but some other people's work show that FeO could fractionate it from the mantle source to the basalts. So actually, there are some debates about that. So this is one debate that this is one approach of doing that. It is basically doing this forward modeling. So you guess the composition, then look at that with different temperature pressure. How does composition evolve in the melts under different conditions? And another approach they mentioned about in the paper is that, okay, you could just know the melts composition, then you're trying to map what the type of the minerals that could coexist with that. So each method has its pros and cons. But by using a software, I think the advantage, not only for MAGMARS, as well as MELS, as well as for all the other softwares, is that they're basically solving the thermodynamic equations. And the advantage is that we need to do that iteratively. That is, for example, you solve one equation at 1500 degrees C, and then you're going to use their results and then to as input values for the next equation at 1495 degrees C. And then you use the result at 1495 degrees C, and then you input that at 1490 degrees C. So basically do that iteratively. And the software help you to do that so that you could monitor how the magmas really cools or how they're really being heated up and produce partial melts, so that you have this different step process, so that you could know, you could simulate the conditions that are very likely to occur in the Earth or planetary interior. So that's the advantage that they are doing that. And of course, this work they are going to show some more advantage that they would like to point out that the MAGMARS by applying to the FeO-Rich domain of the Martian mantle, what are their advantages are. So okay, I've been speaking a little bit for too much. So Arka, please go ahead.
The way they've approached this problem is that with the so previously also people used to do laboratory experiments and they use the Gibbs minimization softwares that we have, like you said, the p-melts, the melts, but the different experiments had a huge variance in their results. So it was very difficult to correlate or compare the results. And especially this happened when they were dealing with FeO-Rich compositions, when they started with FeO-Rich bulk. So that was the beginning, or that is what the paper tries to solve. So MAGMARS is a combination of new experiments. It performs two sets of experiments, and then it has an experimental approach and a modeling approach. There are two sections to this problem. The MAGMARS software can constrain the physicochemical temperatures, like physicochemical conditions like the temperature, pressure, the bulk composition, and it can simulate the melting processes that produces rocks which are similar in composition. I shouldn't say rocks, produces compositions which is similar to those found in the Martian surface. So a basic introduction to MAGMARS, I've already dealt with the first part, that is what it means to understand the Martian mantle composition, or Martian mantle evolution. So how people was trying to solve the problems previously, they had two approaches. The one set was called the direct approach, and the other was called the inverse approach. So what happened in the direct approach was these studies were performed on the model compositions which are representative of the primitive mantle, and in and generally it was not possible to extrapolate. It was not possible to extrapolate the results directly to constrain the melting of other mantle reservoirs. For example, the depleted mantle reservoirs or the metasomized mantle sources. And the problem with inverse approaches was that it could be used for other mantle reservoirs, but in certain cases, it was not able to constrain the mineralogy of the mantle source or and not the bulk composition. Uh, People tried to use the existing thermodynamic minimization softwares to run their for the modeling approaches of the Martian mantle. Uh, but the problem was that they usually had an overestimation or an underestimation of the values. Although p-melts up to some lower mantle fraction, up to some lower degree of fractionation shows some correlation with the results of MAGMARS, but it doesn't confirm entirely, and that's why this modeling approach was taken. So, dealing with the first leg of this publication was understanding the experimental approaches they have taken. So, in the first series of just in the first series of experiments, they have done 5 experiments, and they have used the starting composition as they have referred to a paper called Debris and Winkel, 1985, and they have used the starting composition as same as theirs, and in 2015, when the author of this paper released experimental protocol, he used the same protocols, and they did this experiment. The difference between this experiment and the second experiment is that the first experiment was done at a slightly higher pressure, ranging from 2.4 to 2.66 gigapascal, and for phosphates or P2O5 was not induced. In the second series of experiments, those are basically the reversal experiments where they have mixed a basaltic and a peridotic mixture together in a sandwich form, and this was done with the so it helped this experiment practically helped us to understand the effect of phosphates in the melting in the melts. Basically, when phosphates are present with silicates, they can form they can actually polymerize, and it doesn't actually follow the normal silicate fractionation that we see in Earth. So this with this results and results of these two experiments and results from certain other experiments, they went to model this and they came up with a software called MAGMARS. So the basic framework of MAGMARS is very similar to that of, they have referred to a paper, and that is called Clinzer and Grove in 1992. This, it follows those family of models, and it can, and it uses the thermodynamic equilibrium. The constraint, they use it by a equation that was given in Collinet's paper in 2015, that it is a pressure dependent melting equation, uh, and to use the, and to find out the partial melt composition, they use the simple batch melting formula, and and then feed it to the Gibbs equation. However, the compositions of SiO2s, calcium oxide, iron oxide, and MgO, they are calculated based on a multiple linear regression. And this linear regression is, this model linear regression equation is uses the parameters, or is parameterized by a calibration of a database of large experiments, and usually they weight it. So they give the highest weight to Collinet's database in 2050, and they have a multiple databases or papers from where they have taken the data, which they weight accordingly, and the weight percentage is different for different databases. So coming to the results from the MAGMARS, so what we can see here in this picture is basically the figures marked A, B, and C. These are basically the three types of melting processes that it can uh, it can deal with. This model can deal with, that is near fractional polybaric process, the batch melting process, and the near fractional isobaric process.
Okay,
Uh,
okay. Could you remind everyone what is fractional melting and batch melting? I think
okay,
most of us know,
so
but I
yeah,
think it is good to do some basics here. Yeah.
okay. So batch melting. So when supposedly that I have, so the mantle, its composition is not homogeneous. So basically, it has different materials in it, and those will have different melting points. So while I am melting, while certain substances have melted, others might still be in the crystal form. So batch melting is when the melt is solidified back, like entire thing is melted and then it solidifies. And fractional melting is that whenever the first material is melted, it moves out of the system and we are dealing with a new system again. So fractional melting is basically where as soon as the melt is formed, it moves out of the system, and the composition that we're dealing with now is a new composition. Whereas in batch melting, we consider the entire thing to melt completely and then deal. I think that is nearly what is, if I'm not wrong.
Yes. So batch melting is a closed system. So fractional
Yeah.
melting is an open system. The melt moves out of the system, then start a new system. For batch melting, then the melt still stays within the system. Okay, go ahead.
So basically, so over here, now coming down to the figures, D and E, that is the two graphs over here. So what they represent is basically the figure D represents the pressure temperature melting conditions during decompression melting. So what is decompression melting? So melting happens in the mantle due to mostly three reasons. I remember two. One is decompression, another is injection of fluids. So when the uh, mantle material is coming up, so pressure decreases down. So there's a decrement of pressure, which leads to a volume expansion and melting happens. Somehow near that, that is the basics. Uh, so what they have shown is that what is interesting over here is the intersection of the adiabat over here. So just a excuse me. So melts are so the temperature at which it happens is around 1410 degrees Celsius, where they intersect the temperature and the effect. We can see the effective solidus. The melts are continuously produced and extracted up to the base of the lithosphere along the color gradient. So if you look at the color gradient, you over here it is the melt percentage, over here wet percentage, and it touches the base of the lithosphere at around somewhere more than 25% is the fractional is the crystal melting. So the melts increment. So as the melts increment, they do not re-equilibrate with the mantle at a shallow depth and are pulled directly into the crust. That what it means is that there is no influxes and it goes to the crust and basically forms this solidified thing. This happens during the isobaric melting, and MAGMARS simulates this. So they have given two conditions. Actually, it was my difficulty to find out that what is the difference between D and E. Basically, I both were for depleted mantle. So basically, they were for two types of. One was for polybaric and one was for isobaric conditions. Uh, Coming to the next part, this is another thing. So as I am, if I put it in full screen mode, is it visible? So another one of the results of or use of this MAGMARS software was they made a liquid thermobarometer, and as we can see that uh, from here, it's the first figure is a standalone thermometer, and figure B is a standalone barometer, and we can see the accuracy of this. The dashed line represents a plus minus of 5 degrees Celsius and 0.5 gigapascal. And between all those legends that you see, they are basically experiments from other papers, how they fit in, and experiments from this paper. So, uh, so this actually helps. These parameters, they have also given an equation. They have actually used a particular equation from Lee et al.'s paper in 2009, and they have used that equation. But what they have done, they have added a phosphate correction, that is P2O5 correction factor, to both the temperature and pressure calculations. So those equations are available in the paper. Like they've given the entire equation over there, and this actually can give us the prerequisites for the input that is required to put in MAGMARS software. So if we compare this over here, what they have done is they have compared the isobaric melting of Martian mantle with the starting bulk composition as they have taken. In figure A, they have shown the melting temperatures in batch and fractional and how they vary with other papers, and they've made with other experimental studies previously. From figure B to D, they give a melt compositions. They give the comparison between experiments of Collinet's work in 2015 and and some other works from Berica and I don't remember, a 1994 paper they have given it. 2004 paper was there. So these experiments were carried at different pressures. The temperatures were calculated with different thermometers for lozolite, Herzbergite, Dumit, and the transitions in the melting temperature curves occur after the clinopyroxene and orthopyroxene have been observed. So the curve that you see over here, it happens after a particular phase change, and this is all about this particular. And second is, what were the two drawbacks we talked about? We talked about the two drawbacks. That was one in the existing experiments, and another was with the Gibbs minimization tools. Why we couldn't use them? So this is a comparison with the Gibbs minimization tools that are available. One is with the PMELS, another is with the Holland's database. And what we see over here is that, interestingly, that so if the FeO concentration of the primary melts produced by melting a Martian mantle, the comparison of different models, we can see that P-melts shows which it overestimates the FeO concentration by up to 9 weight percentage. Perplex with Holland's database reproduces the experimental melts most accurately over here. And all these calculations were done with near fractional isobaric conditions. So another application, one of the applications that they have shown is that they have used a particular basaltic composition that is of the primitive math, that is adrenodac basalts, assuming that the mantle source was depleted with and had a low potassium oxide by sodium oxide ratio. They were able to show the model for that particular basaltic composition, and which was in conjunction with other experimental studies and with what we found from the rover data. Depending on whether olivine was there or not, they could show the results. One of my doubts in the paper was how does the change in olivine actually affects these two soliduses, and how why the adiabates cut at different places. So maybe we can discuss. Coming to the summary of this paper, so these are the practical pressure ranges at which the experiments were performed, and they considered the phosphorus oxide or the phosphates influence in the melting processes. Their experiments, they perform new experiments, and their database is made up of new experiments as well as old experiments, and with weighted values. They provide us with an updated thermobarometer, which helps us to calibrate the input values. Uh, it can work both on primitive and depleted mantle and other mantle sources, and it can also constrain all the thermodynamic variables. And in future, the author says that this model will be coupled with convection models. So that would be all. Thank you.
Okay, thank you, Arka. So any questions from our participants today? Okay, could you turn to page 12, Arka?
Page.
Page 12. 12. It may be earlier. Okay. For this one, so what they are showing, not a very, so basically they want to have so they basically want to make the models more self-consistent with the experimental results, but we can see that FeO keeps relatively flat if FeO concentration is about 20% or higher. I think 15% it doesn't fractionate too much. But if FeO is very low and 5%, then so they mean, I think they mean the composition of the melts. So basically they are incompatible. Okay. Okay, but that they say, okay, all the models works well at low pressure, but when it goes to 2 GPa, then it begins to have some problems in P melts. All right, so MAGMARS looks better. So basically, okay, but in my understanding that in this paper, what they did for the high pressure experiments they only did this experiments up to 2.6 GPa.
No,
So
they used two sets of experiment. The first 5 experiments they did was at higher pressures, like 2.4 to 2.6. But the second set of experiments was done at 1 GPa.
Yeah, 1 GPa. So basically they didn't add too much high pressure experiments. So So could you remind me that what's the difference they have in this MAGMARS when they do the calculation of thermodynamic equilibrium compared with PMLs? Because this difference doesn't caused by the addition of 4
In
GPA or 5 GPA experiments, but
females, they overestimate the FeO concentration by, or the FeO percentage by almost 9%. Uh, in comparison with magmas, and also magmas, the model they make, they just don't base it on the experiments that they have done. They also use the database from Collinet's paper in 2015 and a bunch of other papers. And they have, what they have done is that, for example, they have Collinet's paper and paper ABCD. So they have weighted the data from Collinet's paper, they have weighted it the most, and the other papers they have weighted relatively. There are almost many papers, so I don't know what is the logic behind weighting those, giving different weight percentage to those papers. And then that is the input of magmas, like that is on the framework of magmas. So magmas doesn't just only use their experiments in this paper. It is one of the part, but
so if I make a bolder guess, then I would expect at the Collinet 2015 paper, they would include some high pressure experiments up to around 5 GPA. That's what they are trying to show here. Okay, so could I say that thermodynamically they don't have some fundamental difference in writing equations, but only because they have different data sets, thermodynamic data sets between PMLs and MAGMARS, so that when they refit the thermodynamic equations, then they have slightly different parameters, of course, that lead to different predictions.
absolutely, because they use the same Gibbs energy minimization. Basically, they also their work. This MAGMAS model is based on one of the family of models by Klinzer and Groove in 1992. So their fundamental thermodynamic equations are also same. The two differences that the way they have done the experiments, and second is that they have used in the second set of experiments, because P2O5 is very much abundant in Martian mantle. Not as in case of our case, we don't have that much of P2O5 concentration in our mantle. So they have used that correction also. So that is one more thing that they considered. So these are the two changes in their experiments.
Okay.
That is my
Could you remind
understanding.
me, did the MAGMARS wrote in Python or is in Fortran?
That I have not seen, because they have all mentioned it in the supplements. I have not gone through the code of MAGMAS. Like, they do have the code. I can just give me a minute. Let me see. They have used it in MATLAB.
Okay. Okay. Hmm. Okay. Hmm.
They
Okay.
also have it on GitHub.
Yeah, go ahead.
Okay. So this was one of the problems that I faced, understanding that what is happening with if olivine is going out, why are the solidus is changing. I understand they have given to some equations over there, but I couldn't understand the fact that what exactly is happening. Like, also I didn't understand that why did they try to use this particular basaltic composition to show the primitive Martian basalt composition. So I didn't get it.
I think
This
that's
was my doubt.
I think that they're trying to say that that's the possible uh, Martian mantle composition. I mean, then they are like DW85. I think they're probably trying to say that that's the bulk Martian composition. And so that's the solidus. So basically above that, then you begin to generate the melts. Then you have the points here, which they show relatively low melt fraction from 0.1% to about, like, say, 10%. So what are those points? So when they say they made some colors, so from dark blue to light blue for those 2 points, for those two curves. what are they? So is that what they are simulating? What could be generated by the
Yeah.
proportion
So
of
if
melt?
you see the heat map on the right hand side, so that is the melt wet percentage.
Mm-hmm.
So ideally it goes from 0 and it is somewhere near in 10, 5 to 10 or a bit more than 10 when it reaches the lithospheric crust over here. And when it is with olivine and when it is a depleted mantle source over here, it is somewhere around 5 to 10 or a bit more than 5 around.
But that is they both assume, I say, uh, okay, they assume the third one. Okay, so in the basically they are using the lithosphere temperature, which here they assume actually is relatively high. So how much melt that could be generated by that? And then the given curves with the 76 and 81, showing here two lines. That's a more on a vertical direction. So for those two, they are trying to say what the number stands for. Is it the mg number of olivine?
Yeah, it is the MG number 76 and MG number 81.
So basically, then the higher mg number it is, then the less iron it's going to have. And then, of course, the higher melting temperature it should be. So why they are putting those two curves here? So they are trying to 76 and 81. But that two lines, 76 and 81, looks more like certain geothermal gradient that they're trying to follow. I didn't understand that. I don't understand that. I don't understand that. Let me check.
Actually, they also have a graph like just before this in the paper, which I didn't give it. So
With and without. Okay. 81. So it's just a simple whether they think this Martian, like I said, anti-rhodetic basalts of Mars, whether they fractionated with or without olivine. So basically, 76 is without olivine. So that's how melting conditions. Right. So that's how they're. Hmm. Okay, so for 81, basically along that curve, so then they are going to have some compositional change because they're going to fractionate about 17 with a percent olivine along the way. Of course, it is going to change composition of basalts, like they represent low probabilities. So they think that's the two different end member. Okay, they do also mean mg number. So the higher mg number you have, then even the fraction is an olivine, that also makes sense. The source of that, so that how the source of that comes out. But also they are trying to say, okay, that's the curves. That's the likely direction. But I don't know why they put those two lines here, 76, 81. What's the rationale they have here to say, okay, those two curves must be going this way?
So actually, if you have the subsection 5, they have wrote about this entirely, but this entirely went tangent to me, like what they were trying to do. That the mantles, I understand that adirondack basalts are a debated topic, that whether they're the source of Martian mantle. They are trying to prove that it is, but how they have done it, that went tangent to me. Like I couldn't understand what they've done actually. So apart from that, this was all from my end.
It's also confusing to me now. How they decide to choose that? Perhaps I could ask the speaker to clarify on this if I did not fit the route in the coming 2 days. It's an important, it's an important graph they're trying to convey the information here. Another thing is about the lithosphere temperature range. Maybe that's from inside the mission, I'm not sure. Uh, Any other questions from other participants? Okay, if not, then let's thank Arka again. Could everyone open your video as a show of appreciation for Arka for leading the discussion? And then we're going to turn it off in 30 seconds. So everyone, could you open your video? So we see different hotels. Okay, that's about it. See you everyone on Wednesday for the speaker.